Hello everyone, it is your boy Benji. We are back, and today we are taking a look at simple linear regression, which is a pretty fundamental concept in machine learning and statistics, and sort of falls under the umbrella of supervised learning. And I think it's probably best understood just kind of flowing through an example. So you might imagine that you've got some data points like we have here, so all of these blue points. And the goal of simple linear regression is to find the best fitting line through all of these points. So that might be the one that we've drawn here. And so we start with this line, which represents a relationship between input and output variables. And for this, we're going to use the classic formula y equals mx plus b. And so this will represent our line that we think best fits these data points. And we'll use this line to make predictions. So if you give me the value 1000 as input, I might say, hey, this is what the output should be. And we might have some sort of data point, so the actual data point is here. We'll be off a tiny bit, but that is totally alright. The idea is that across the board, we're pretty close to matching all of the data points. So you can imagine we first start off by initializing the m and b values. So in y equals mx plus b, m here is representing the slope and b is the y-intercept. And then in machine learning, it's not uncommon to here wait for the m value, and then also b would be your bias term. So slope and weight are interchangeable, and then bias and y-intercept are also interchangeable. So you might start with the line. In this case, we have m is 0 and our y-intercept is 0, so we just have a flat line like this. And we might say, okay, this is not great. How can we update the values of m and b such that this line gradually gets closer and closer to being this best fit line? And so that's totally the idea of simple linear regression. Is let's slowly iterate and make these values of m and b slightly more optimal to match these data points a little bit better. So what we can do to find these best values of m and b is we can actually introduce a cost function. So our cost function for this one will be MSE. This is a pretty common cost function, and it's just the mean squared error. And so it's just adding up all of the differences between the actual value and our predicted value, squaring them, adding them, and then dividing by n to get the average. So what it's doing is it's averaging out the squared differences between the predicted value and the actual value. So yi here is the actual value given an input x, and then y hat will be our prediction. And so just expanding this a little bit, y hat, our prediction, is just exactly what our line would output. So it's just this formula, mx plus b for any xi. So if we scroll down a little bit, we can actually see that this mean squared error function is quadratic, and so visually this will look like a parabola. And so in simple linear regression, the idea is we can take the derivative of this cost function with respect to m, the slope, and also to with respect to b, the y-intercept or the bias. And then we want to, with this slope, we actually want to see if we should decrease m and decrease b, or increase m and increase b. So the slope of the tangent point with respect to m will tell us in which direction do we need to travel, do we need to change m basically, to reach this minimum cost function point, this little orange point here. So if we take the derivative of the cost function with respect to m here, we would see that this is a negative gradient or a negative slope. And so this means that increasing m will actually get us closer to this minimum value of the cost function, this orange point. And so we actually want to increase m in this case, just a little bit. If we start here with the b value, so we take the derivative of the cost function again, but this time with respect to the variable b, our y-intercept, we see that our gradient is actually positive. So it's heading up in the upwards direction, which means that if we increase b, we're actually going to be increasing our cost function output, which is bad. So in that case, you actually would travel in the opposite direction of the gradient to approach this minimum point on the cost function curve. One thing to bear in mind is there's a value we'll see later. I think it's alpha. It's a hyperparameter, and so you can actually just change how big the jump is that you take when you're approaching this minimum value. And that's super important because sometimes if you have a tangent like this one, if you have traveled too far, you might go so far that you end up here on the parabola at a point that's even further away from the cost function from where you started. So sometimes you want that alpha value to be pretty small, but if it's too small, it could just take so many leaps and you make no progress, that you you basically stay in the same spot. So there's pros and cons to having a big or large value of alpha hyperparameter, but again, we'll see that in a little bit. So I think next up, we'll take a look at actually deriving the gradients or the slopes of the tangent to the cost function curve with respect to m and b. So we'll start with the derivative of the cost function with respect to m. So to make it a little bit simpler, we'll just get rid of any of the summation stuff for now, and we'll just take a look at taking the derivative of what we are summing up, which is the difference between our actual value and our predicted value, and then all of that squared. So the derivative of this with respect to m is this, which is just super simplified. We're just factoring in this negative sign, distributing it, and then we can just use the chain rule to take the derivative of this whole monstrosity. So this 2 will come out front. We're just taking the derivative of this outer function, and then we're keeping the input of that function the same according to the chain rule, and then we're just multiplying this by the derivative of the inner function. Definitely, take a look at the chain rule if this is super crazy, but we'll just go over this a little bit quick. So with respect to m, yi is just a constant, and that's exactly the same for this negative b term. But this inner term, so mxi, the derivative of that with respect to m is actually negative xi, because if xi doubles, then m also doubles. So this actually is the sort of output or the result of the derivative of this term with respect to m. So that's what we see here. So we're multiplying by negative xi. And then just popping this back into the summation equation that we saw earlier, we have the sum from 1 up to n of this term that we've derived here. So negative xi times the difference between our actual value and our predicted value, and then we're just dividing all of that sum by n to get the average, and then multiplying by 2, and the 2 came from that exponent rule when we were doing the chain rule earlier. B is super similar. Same things are going on. We take the derivative of this, but with respect to b this time. So yi and negative mxi are actually constant terms, and then in b we just have this negative 1, which we see here. So that's the negative 1, and then we also applied the exponent rule, which is where this 2 comes from. So we also plop this back into our summation equation, and then we get the derivative of the MSE, the mean squared error function with respect to m over here, and then the same but with respect to b over here. So now we can actually use these gradients to update the values of m and b. So we first find these for any given point, and then we update the m and b values. So to update the m value, we're just going to set m new, so this is going to be our new m value. And all it's going to be is it's going to be equal to the old m value. So in this case, we initialized m and b to 0, so maybe for the first iteration we could say this is 0. And then we're going to subtract away from it alpha. So this is that hyperparameter that I was mentioning earlier. And we're going to multiply that hyperparameter by the gradient of the MSE with respect to m. So this right here. And so, as mentioned before, if our gradient is positive, then that means we're somewhere over here, which means our tangent is positive. And so we actually want to decrease this m value so that we can approach this cost function here. The minimum of the cost function. And then it's pretty similar on the other side. So if our m value is over here, we'll have a negative value for this gradient, which means we actually want to subtract away a negative. In other words, we want to increase m so that it moves closer and closer to this minimum cost function value. And so hopefully after doing this, our m value and our b values are both a little bit closer, so they might just be a tiny bit closer. And then what we want to do is we want to use these m and b values and just go back up to the top. And so instead of m being 0 and b being 0, they'll be set to whatever we got at the end there. And then we'll just go through this process all over again. And so we'll update m and b values gradually along this cost function curve to eventually reach a minimum. And then hopefully you'll have m and b values such that your line is like this one, the best fit line, matching pretty closely to all of your data points. And then with this line, you can make predictions. So maybe X here, we're kind of talking about years, and then we have some sort of output. Maybe you have a toy factory, and they, over the years, have sort of increased the number of toy models they're making. Maybe you could predict far into the future. So maybe if this is year 1000, maybe up here you could predict how many toy models they'll have in year 2000. Yeah, so something like that. So that's extrapolating, kind of going beyond your range of points, but you could also interpolate. So if they're missing some data points, you could say, hey, maybe in year 500 they had this number, and so you can start making predictions. And so that is simple linear regression. Thank you very much. Cheers.